So, now let us see Fourier's law of steady state heat conduction in one direction. So, now we are concentrating on conduction, heat transfer by conduction. So, we have a law, Fourier's law, that is for different types of heat conduction for steady and unsteady also. Presently, we are interested in steady state heat conduction and only in one direction. So, steady state heat conduction. So, first of all, we have to understand the meaning of steady state. So, in a very short term, steady state means equilibrium. So, the meaning equilibrium may be misguiding. So, we have to give an example. So, steady state means, suppose just imagine a traffic. So, this is a traffic and you see here. So, this traffic has some sections like this. So, here you have one width, the road width is, this width is large, here come, and here there is a traffic signal, and here some signal is there and some barrier or some checkpoint is here. So, now initially suppose here is also a red signal. So, when this signal is green, the traffic will immediately move, and you see the traffic will be initially more here, and suppose here there is no traffic. So, here there is no traffic, but here there is more traffic. Why? Because here then when red signal was there, on the traffic went out. So, that means the traffic is coming out. So, here we observe that here 10 cars per second are entering, but here I am not finding any of the cars. So, here there is a heat current entering, but here there is no heat current. But what happens after some time, when this traffic will be 10 cars here, and you see the traffic will be here. So, you see what I mean to say steady state is that, so if 10 cars are entering, the 10 cars are per second are leaving this junction also. 10 cars are entering and here 10 cars are coming. You might find that here this road is width is less. So, here car must be moving with larger speed and here with lesser speed. So, when I say that a steady state is reached, that means that throughout whatever however car per second is crossing here and here, that is the same. The speed of the cars may be different at different locations, but the amount of cars coming, the flux of cars at any of the cross section is going to be the same, so that at any junction more cars should not accumulate. So, the rate at which the car at any junction, the car is coming here and the car should leave that junction, that state is well maintained. That is what I mean by steady state. That does not mean that here the flux or per unit length width will be same and here will be same. So, when I say steady state, that means whatever the cars are coming, whatever the heat are coming at one cross section, that must leave at all the cross sections. So, incoming and outgoing must be same, so that accumulation of anything, whether cars are coming or heat is coming or mass is coming, anything, that means at steady state the incoming and outgoing must be same, so that there is no accumulation taking place at any of the place. That means that is what I said, the system is in equilibrium or something. This equilibrium language is used by chemists. Now, let us see a one dimensional flow. So, let us see that this is a uniform cross sectional conducting rod, this is heat conducting rod, and this now this temperature is theta 1 and this cross section is theta 2. So, we see that this shaded cross sections is, this cross section is maintained at theta 1 and this cross section is maintained at theta 2. I let this length be L and this area be dA. So, this length L and dA. So, this is a rectangular cross section. So, according to Fourier, at steady state heat conduction, the rate of flow of heat, we call this as heat current. The rate of flow of heat is found to be directly proportional to the area of cross section and temperature gradient So, suppose I say heat current is defined as dq by dt, the rate of flow of heat, or I can call in shorthand as I, heat current as I, and temperature gradient that is how the temperature varies with position. So, I say it is d theta by dx. So, according to the law, dq upon dt is proportional to area of cross section and d theta by dx. So, thus dq by dt is equal to minus Ka d theta by dx, where negative sign indicates that heat flows from higher temperature to lower temperature. So, heat flows from higher to lower temperature. Here K is called the conductivity of the medium, is called the conductivity. We also call it thermal conductivity. So, is called the thermal conductivity, I can write thermal conductivity of the medium. So, this is very important result. dq by dt is equal to minus Ka d theta by dx, where theta is d theta by dx is the temperature gradient. So, now let us see that this is applied to a rod, conducting rod. So, this is a conducting rod of uniform cross section A, with this is at higher temperature. So, this is hot and suppose I say this is cold. So, heat flows in this direction from theta 1 to theta 2. So, if I have to write like this, for this the rate of heat is I is equal to minus K A. Now, temperature gradient means the rate at which, not rate means dq by dt is called rate, but dq by dt will be called gradient. So, here gradient of temperature is required, how temperature varies with position. So, you see this is at higher temperature. So, we will write this as theta 1 minus theta 2 by L. So, since this is minus, so we can put it that this is the heat flows in this direction. So, this is theta 1 minus theta 2. So, actually temperature gradient means the final minus is, so I will write this as theta 2 minus theta 1. Now, as I have mentioned, this is hot, so theta 1 is more than this, so we can bring minus, so that is we got this. So, now you said you recall this definition, this is similar to the current conduction in current electricity. We can further write this as I is equal to delta theta by L by K A, and then it will be written as RTH, where RTH is equal to L by K A. So, RTH is called the thermal resistance of the conductor. So, you see this RTH is equal to L by K A. So, when I apply my Fourier's steady state heat conduction law in one dimension to a uniform rod, then I got that the heat conduction formula will be given by this, and thus this conductor will offer resistance to the flow of heat. That resistance will be called thermal resistance, and that is given by L by K A, where K is the thermal conductivity of this rod, A is the area of cross section, and L is the length of this rod. Now, let us see that if we have different type of materials, this rod or different slabs, they are pasted side by side, okay, in series and in parallel, they can form a composite material. So, what will be the equivalent thermal resistance of this composite material?